Hello, everybody. My name is Asante, and today we'll be talking about this week's experiment, constant velocity. To start the experiment, I created a computational model like follow using the following code in GlowScript, using a while loop here, running this code to get this shot and these graphs showing the computational model. And then after that, I created a real life model of a table moving along, of a ball moving along a table. And I put that into Tracker and collected data from it and plotted that into graph. And afterwards, I plotted a graph showing the motion of the computational model in gray and the real life model in blue. Both lines are straight, meaning that both models have a constant velocity. There's a minor difference between the computational and real life model that might have been caused by environmental factors in the real life model. Conclusions to be drawn from this: when no net force is applied to the ball moves at a constant speed in one direction, i.e. constant velocity. This proves Newton's second law, which states that the final velocity is equal to the initial velocity plus the net force divided by the mass multiplied by the time interval delta t. Since the final velocity is equal to the initial velocity, the net force is zero, so the velocity is constant. And along the vertical axis, the weight of the ball is equal to the contact force on the table. Overall, there's no net force acting on the table. Hypotheticals: if more friction were added, the ball would slow down. If air was blown from in front of the ball would slow down. And if air was blown from behind the ball would speed up. In these three situations, a net force is being applied, therefore the velocity would change. If the ball direction was switched, the position numbers would be negative and the gradient of the line would be negative because the direction is changed. Assumptions made while doing this experiment: air resistance and friction from the table are negligible, and the ball travels only along the x-axis. Thank you for your time.